All right. So here we go. So reliable delivery. This is a definition that we wrote down before. So we said, let P1 be a process that sends message M to process P2. If neither P1 nor P2 crashes, and then we put this asterisk here, then P2 eventually delivers M, the message. So I put this asterisk. So what does that asterisk represent? I mentioned last time that different people define reliable delivery in different ways. So what goes there is another part of the definition, which is, and not all messages are lost. So do we need that part that says, and not all messages are lost? Well, it depends, right? If we're working under the crash model or the omission model. So if we were working under the crash model, then the only kinds of failures that can occur in the crash model, which we talked about last time, are processes crashing, right? And so we need to have this disclaimer if neither P1 nor P2 crashes, but we don't need to have this other disclaimer about messages being lost. On the other hand, if we're in the omission model, then we could have the crashing or we could have messages being lost. So then we need to have that piece in there as well. So we need to have this part if we're working under the omission model. Which do you think is more realistic, the crash model or the omission model? So we're getting some different answers from different people. Some people on Slack are saying crash. People on Twitch are saying omission. So I would say the omission model is more realistic because the omission model, recall the crash model, recall that crash failures are a subset of omission failures. So if we handle omission failures, then we're handling crash failures as well. And omission failures are actually quite common in practice. So we need to have this extra bit in here as well. So we'd better have that assumption. Okay. Although this is a little bit annoying that the definition of reliable delivery differs depending on which fault model we're working in. So we'll come back to that later. All right, how are we going to implement reliable delivery? If Alice has to get a message to Bob, how can she do so reliably? Any suggestions? Yeah, okay. Handled by TCP. Right, but let's say that we're implementing TCP. Yeah, so there's a good suggestion in chat. Just keep sending messages over and over until you get an ACK, right? So if Alice wants to send a message, then she puts it into some sort of send buffer on her side, right? So she sends the message. And it goes into the send buffer. And she has a timeout on her side. So the algorithm goes like this. Whenever the timeout expires, you send what's in the send buffer and you reset the timeout. But you don't delete it from the buffer yet. And then you just keep on sending the message, right? And then, maybe some of those are lost, maybe some of them are slow, whatever. But at some point, hopefully a message will get through. And then at that point, Bob will send an acknowledgement. And then if you receive the acknowledgement, then you can stop sending the message and delete that message from the send buffer. So some people are asking in chat, what is an ACK? ACK is just short for acknowledgement. So this is the acknowledgement message from Bob. So whenever an ACK is received for a sent message, you can just delete that message from the send buffer. What issues are there with this implementation? Well, somebody already pointed out in chat that this doesn't solve the two generals problem that we talked about last time, and indeed it doesn't. So Alice can be sure that Bob got the message, right, because she gets the acknowledgement. So there's certainty on the sender's side, but there's not certainty on Bob's side that Alice got the acknowledgement. So it doesn't solve the two generals problem. So one issue with this implementation is, well, what if the ACK gets dropped, right? What if this message here gets dropped? Then Alice will keep sending. We know that eventually some ACK will get through because the specification of the protocol we're trying to implement has this, and not all messages are lost. But what would it mean if Bob's ACK was dropped, right? It would mean that Bob gets Alice's message twice, or it could mean that, right? So, or even just if even if some of Alice's messages were slow, right? So we could have a scenario like this. Notice we're not talking about, we haven't said anything about FIFO. We're just talking about reliable delivery. So in principle, some of Alice's messages could cross over in the channel, right? So we could get something like this, where Bob would send it. Maybe Bob would send an ACK here. This message up here was slow. Alice gets here, right? She hasn't received any ACK yet, so she's sending a second message. Bob ACKs the message here. But then Bob receives the message again. So Bob gets a message twice in this setup. Or this could even happen, let's say that this, even if you did guarantee FIFO, what if this message up here just got lost for whatever reason? Do you think it's a problem for Bob to get a message twice? Well, I think it depends on the message, right? So in fact, when we were talking about workarounds for the two generals problem, one of the workarounds we came up with relied on sending the same message again and again until we got an ACK, right? And assuming that it would be okay if more than one could get through, right? So it looked like this. Alice would send attack at dawn, attack at dawn, over and over and over. If Bob got one, he would say, okay. So we're imagining here that Bob actually got the first message from Alice and he acknowledged it. But maybe it took a while for the ACK to arrive, so he got a couple of extra copies maybe of the attack at dawn message from her. But do those messages actually change his mind, right? Like, is he gonna say, oh, she said attack at dawn twice, does that mean she doesn't really want to attack at dawn? No, in this case, it's not gonna mean anything different for Bob if he gets a duplicate of the attack at dawn message. But in general, some messages have this property and others do not. So let's say that you're assigning a value to a key in a key value store, right? So say I'm a client here, and here's the key value store, and I send the message. First, let's say I send the message assign 3 to x. And let's say that that one gets duplicated. So if that message gets duplicated, is that a problem? Yeah, no, I wouldn't say that this one is a problem, right? I get the messages on the key value store side, and I get assign 3 to x, and then again, assign 3 to x. So is the result going to be the same as if I had only done the assignment once? Yeah, it would. On the other hand, if this were the message, if the message were increment x, would that one be okay to duplicate? No, it would not. No, because doing increment x twice is different from doing increment x once. So the word for a message that it's okay to receive more than once, or a function that it's okay to run more than once, is idempotent. So mathematically speaking, we say that a function f is idempotent if f of x equals f of x, which means that it's equal to f of x, and so on. So assigning to a variable like this is idempotent, but incrementing a variable is non-idempotent. And idempotence ends up being really important in distributed systems because, generally speaking, a good way to make sure something gets done is to try to do it a bunch of times until at least one attempt succeeds. And this, so it's going to be useful if we can design systems in such a way that messages are idempotent. So this isn't always going to be possible, right? Because sometimes we need operations that aren't idempotent. But generally speaking, we'll have an easier time of it if we're working with idempotent operations. So what this has to do with reliable delivery is that in order to implement reliable delivery, we typically need to deliver a message more than once sometimes. So reliable delivery is sometimes called at least once delivery. Okay, so reliable delivery is at least once. What about at most once delivery? How do you get that? Yeah, it's really easy, right? Just send a message. If it arrives, great. If not, great, right? Or even better, just don't do anything. So at most delivery is trivial to implement. Okay, so we got at most once, and we got at least once. What about exactly once delivery? Is it even possible? Yeah, somebody's asking on Twitch about the network model. So yeah, for everything we're talking about here, we're assuming the asynchronous network model. So I am not aware of a formal result that says that exactly once delivery is impossible. But I will say this. When people out in the world claim that their system provides exactly once delivery, usually what they mean is that the messages were idempotent anyway, or that their application is written in such a way that it deduplicates messages. So when they say they have exactly once delivery, usually that is dependent on some other assumptions about their system. So my colleague Peter Alvaro has some interesting thoughts on exactly once delivery and the two generals problem and how they both relate to that concept of common knowledge that I talked about last time. So if you want to know more about that, talk to him. Okay, so today I want to start to talk about so we talked about implementing reliable delivery, right? It mostly just means send a bunch of messages until you get an ACK. And because that's the approach that we have to assume that messages may arrive more than once. So I want to get into talking about reliable broadcast now, and that I hope will lead us into a new topic. So this class is mostly about sending and receiving messages. We talk about communication a lot, right? And a lot of the communication we talk about is what's known as unicast communication. So what does that mean? A unicast message has one sender and one receiver. So unicast messages are one-to-one. So we briefly discussed broadcast communication in the context of causal broadcast. So recall that a causal anomaly might look like this. But we talked about how if we used a causal broadcast delivery protocol, and we had tried to deliver this message before that one, then instead the first one would get buffered, right? And it would only get delivered after the one that was causally earlier had been received and delivered. Okay, so we mentioned that this algorithm that we came up with for ensuring causal delivery of messages was specific to the case where messages were broadcast messages. It was a causal broadcast algorithm. Um, so what does broadcast mean? Aside from all the causality stuff, what does broadcast mean? So broadcast messages we're going to say are one to all. And then there's multicast, which means one to many, although not necessarily all. Have we seen any examples of multicast yet? Sure. So our usual picture, well, okay, so one question here is when we say broadcast, when we say everyone receives, do we mean that you receive it yourself as the sender or not? So the question is only interesting if we want to be really, really pedantic about it, right? Because if we were talking about, let's say, this exchange of messages, right? Um, then we're calling that a broadcast message. In principle, if you wanted to say everyone received, then you would have to have a little self arrow here as well. But we usually leave that out uh, because it's not necessarily helpful to be that pedantic. But even leaving that aside, this question of do you deliver to yourself or not? Yeah, the example of a total order anomaly is an example of multicast, right? Because we have two clients here. Client 1 sends to these replicas, client 2 sends to these replicas, but the clients aren't talking to each other. So this is an example of multicast. Okay, so C1 sends to R1 and R2, but not to C2, and C2 sends to R1 and R2, but not to C1. So we aren't going to talk about how to implement unicast messages in this class. We are going to assume that there is a built-in primitive to begin with that lets you send a message from one sender to one receiver. But assuming that you had that built-in primitive for implementing unicast messages, how could you go about implementing broadcast and multicast? Any suggestions? Sure, yeah. You could just implement it by sending a series of unicast messages. So, if I'm Alice and I want to send a message to Bob and Carol saying that Bob smells, then I can send it to Bob, and then almost at the same time, I can send it to Carol. So, under the hood, these are actually separate unicast messages. But the way that I want to think about them is as having the same send event. And in fact, that's the way that we have been thinking of them all along, right? The way that we've been drawing this picture up until now is that we've had a single dot on this diagram with multiple arrows coming out from it. So when we draw multiple arrows with the same start point, we're thinking of the sends as being a single event, which is as it should be. But under the hood, you can imagine it being implemented as this set of unicast messages. And you could imagine implementing this in a transactional way, so that if you so that you could maybe queue up all the sends. But in the end, uh, that's only going to be so helpful, right? Because unicast is the only primitive that you have. So that kind of leads us into this next topic of how do we define reliable broadcast. So, and how do we implement reliable broadcast? So let's define it first, actually. So I'm going to define reliable broadcast this way. We'll say if a correct process delivers a broadcast message M, then all correct processes deliver M. Before we get any further, what do you think this correct process thing means? What is a correct process? Somebody just asked in chat, are broadcast messages also multicast messages? I would say it's the other way around, actually. So multicast means sending to many recipients, potentially all. Broadcast messages have to be to all. Okay, so a suggestion in chat is a correct process is one that isn't malicious. So I think it depends on your fault model, again, right? So if we were in the Byzantine fault model where processes could be malicious, right, then you would certainly need to guarantee that they're not malicious. If you were working in the crash model, then a correct process would just be one that didn't crash. So I mentioned that we had these two different possible definitions of reliable delivery, right? One of them said that if process 1 sends a message to process 2, then if neither process 1 nor process 2 crashes, then process 2 eventually delivers the message. And then we also said, okay, the same thing, but also with this additional caveat that not all messages are lost. And the reason why different people define reliable delivery in different ways is that they're working under the assumptions of different fault models. So if your fault model is the crash model, individual message loss isn't a thing. So if that's your fault model, then it's okay to define something like reliable delivery without mentioning message loss. On the other hand, in the omission model, message loss can occur. So we have to have that disclaimer, and not all messages are lost. And in the Byzantine model, we would have to also say, and neither of the processes exhibit Byzantine behavior. So it would really be nice if we could define these properties in a way that's not specific to the particular fault model that we happen to be using at the moment. So we could do that, right? Like to pause this discussion of reliable broadcast for a second to go back to reliable delivery. Redux. We could define it this way. We could say, if a correct process P1 sends a message M to a correct process P2, and not all messages are lost, then P2 eventually delivers M. So what I've done here is, this is different from the definition I had before. Before I just said that neither P1 nor P2 crash. Now this definition is more general because I just say that I say that P1 and P2 are correct. If we're in the crash model, that means that they don't crash. If we're in the Byzantine model, that means that they don't crash, and they also don't exhibit any Byzantine behavior. So this definition is more general. I've taken the meaning of what it is to be a correct process in different fault models, and I've abstracted over it. So we still had to have this not all messages are lost thing in here, though, because if the fault model is the omission model, or any other fault model that subsumes the omission model, then message loss is something that can happen aside from processes not being correct. So anytime you see a definition like this that says correct process, the next question you ought to ask yourself is, what is the fault model? because that'll tell you what it means for something to be a correct process. So going back to reliable broadcast now, detour over, back to our definition of reliable broadcast. This time we're just going to use this correct process terminology from the start. And we're just going to say this definition is now general enough to encompass any fault model that we might be using. Okay, so I want to talk about how you could implement reliable broadcast. And let's say, just for now, that we're working within the crash model, so message loss doesn't happen, but we have to confront the possibility of processes crashing. So how do we implement reliable broadcast? Let's say we have Alice, Bob, and Carol. Let's say Alice sends a message to Bob and Carol. And Bob successfully delivers the message. But Carol receives the message, let's say, but I won't put the check mark here because let's say that Carol crashes before she can deliver the message. Does this violate the reliable broadcast property that I wrote down? Somebody's saying yes. Yeah, a couple people are saying yes. I would argue that it doesn't, right? Because it's about this correct process piece. So Carol crashed, right? So she's not a correct process, right? So it's okay that she didn't deliver the message because the assumption is just that all correct processes eventually deliver the message. So it's okay that she didn't deliver the message because she didn't satisfy this, this premise of being a correct process. But how about this? So we said a little while ago that broadcast is actually implemented with unicast, right? So even though we would like to pretend that Alice's broadcast message was sent at a single moment in time, in reality, there were 2 points where messages were sent here. So if we were to take this spot and actually like zoom in on it, on Alice, it would actually look like 2 different message sends here. So what if this happened? What if Alice sent to Bob and Bob delivered the message, but then let's say Alice crashed before she was able to send the message to Carol, and Carol went along not crashing. Would this violate the reliable delivery property? What do you think? Yeah, well, I think you could argue that, well, one thing you could argue is that since Alice didn't actually manage to finish broadcasting the message, then it wasn't a broadcast message to begin with. But I think we could do a little better than that. So I would say that yes, this is in violation of the spec. So if you don't like that, I guess you can imagine that every message that's supposed to be a broadcast message comes with a tag on it that says, "Hi, I'm a broadcast message." So even if the sender crashed before sending to everybody, you can tell that the message is in fact supposed to be broadcast. Okay, so knowing that a process can crash in the middle of trying to broadcast a message. So, and the reason why this is a violation of the spec, right, is because, so we say, if a correct process delivers a broadcast message M, then all correct processes deliver M. So this doesn't say anything actually about the correctness of the sending process, right? It only talks about the correctness of the process that delivers the message. Recall that delivering is something that you do after you receive a message. So for the definition of reliable broadcast, there's nothing in here about the correctness of Alice, the one who's sending the message. It's only about the correctness of the processes that receive and deliver the message. So indeed, if Alice crashes here before going on to send the message to Carol, then this does indeed violate reliable broadcast. Okay, so knowing that a process can crash in the middle of trying to broadcast a message, can anybody think of a way that we could still have reliable broadcast? So knowing in particular that there could be a crash right here, right at the moment between sending a message, and now that message is gone, right? You can't take it back. And then you can crash right there before sending the next unicast message that's part of your overall broadcast. Since you can crash at that point, is there still a way that we could get reliable broadcast? Yeah, so some people are starting to come up with some good suggestions in chat. So I'm going to propose the following protocol. When you receive a message, you don't deliver it yet. Instead, you pass it on to everyone else. And only once you've done that do you deliver it yourself. So let's see how that would work. So Alice sends to Bob and then crashes. Bob gets the message, but instead of delivering it immediately, he forwards a copy of it on to Alice and Carol. And then he delivers it. And Carol, when she gets the message, she also forwards a copy to Alice and Bob. And then delivers it. So are there any problems here? What would happen if Bob crashed right here before sending to Carol? Would that end up being a violation of the protocol? Or excuse me, a violation of the definition of reliable broadcast? No, it wouldn't, because then Bob would never deliver the message himself. So the precondition of reliable broadcast wouldn't be met, right? So we're okay. So here's one sketch of an algorithm for reliable broadcast. We say all processes keep a set of delivered messages in their local state. When a process, let's call it P, wants to broadcast a message, let's call it M, it has to unicast that message to all the processes, but itself. And then P adds M to its delivered set. And we say, when P1 receives a message, from P2, let's call it M, so when you receive a message and that message M is in your delivered set, then you don't need to do anything. Because that means you already know about the message. Otherwise, you unicast that message to everybody but yourself and the one that sent it to you. And you add it to the delivered set. So some folks are asking, wouldn't this result in a whole lot of messages being sent? Yes, absolutely. So we'll talk about that in a second. So the way that it works is every process is going to keep track of messages that have been delivered to them, right? So we're going to assume that if you're sending a message, then you know about it. So if you want to broadcast a message, remember we're assuming that unicast is a primitive that everybody has. So unicast is the primitive by which we're implementing things like broadcast. So you can then unicast to everybody but yourself, and then you add that message to your delivered set, meaning the message has been delivered at yourself. You can think of it as having sent it to yourself and delivered it at yourself. And then when anybody receives a message, if they've already received and delivered that message, then they don't have to do anything, right? Otherwise, they pass it on to everybody else, and then they add it to their delivered set. So let's look at a couple more scenarios. So we already talked about this situation where Alice sent a message to Bob and then crashed. Before she was able to also send it to Carol. And we worked around that by saying, well, when Bob receives the message, he's going to forward it on to Carol. So Carol will get the message. Okay, well, what if Bob sends to Carol and Alice? And then let's say Bob crashes before he can deliver the message to himself. Well, is this a problem? It shouldn't be. So now everybody but Carol has crashed, right? Because Alice crashed right after sending to Bob, and then Bob crashed after sending to Alice and Carol. So Carol now is the only correct process. So at this point, going back to our definition of what reliable broadcast is, we say if a correct process delivers a broadcast message M, then all correct processes deliver M. Well, we're now in a scenario where there only is one correct process. So now, whether or not Carol delivers the message will still be satisfying this property. So it turns out that this protocol that I wrote down here, this reliable broadcast algorithm, it turns out it works in general. So you could have processes sending back to wherever they received from, but that's unnecessary. So as an optimization, we can leave out that message. But as some people have already pointed out, this protocol is going to result in people receiving duplicate messages, right? So suppose nobody crashes, right? So then we'd have something like this. So even if we have that optimization that you don't send a message back to the sender, right? If nobody crashes, then when Bob receives this message, he won't send it back to Alice, but he doesn't know that Carol got it, right? So he'll send it to Carol. So then Bob gets to deliver the message after sending it to Carol. When Carol gets this message from Alice, she doesn't know that Bob got it as well, so she had better send it to Bob. And then she gets to deliver it. So even with the don't send back to the sender optimization, we still have duplicate messages here. So Bob and Carol each receive the message twice. Bob receives it here and here. Carol receives it here and here. So something that they can do, right, is keep track of what messages they've delivered. And then if they receive one that they've already delivered, like here, then they don't have to deliver it again, or here. So what about forwarding? No, if they've already delivered it, do they have to forward it again? No. That's what that do nothing in the algorithm is. The fact that they already delivered it means that they definitely already forwarded it too. Okay, any questions about any of this? One person asked, what's the difference between forwarding and delivering? So delivering a message, recall that delivering a message means that when you receive a message, it's as though there's a little mail clerk hanging out on this process here who decides what to do with that received message. So delivering a message means that you then make it available to the process. You are that mail clerk and you get to decide, okay, this message is now available. And you can choose. So delivering is something that you get to choose when to do, which is why it's such an important mechanism for implementing things like causal broadcast, which lets you queue up messages and not deliver them until until it would make sense causally. So that's also a mechanism that we can use here. We can wait to deliver a received message until we forward it to everybody else. So forwarding is just sending to everybody else. So a big idea that I want to leave you with here, which we saw when we talked about reliable delivery, and now we're also seeing with reliable broadcast, is this idea that fault tolerance often involves making copies of things. So in the case of reliable delivery, we were able to tolerate message loss by just sending multiple copies of a message until at least one got through. In the case of reliable broadcast, we're able to tolerate processes crashing by making copies of received messages and forwarding them. So this notion of fault tolerance involving making copies is going to become important as we get into the next part of the course. I'm going to pause here and we'll do a quiz question. So folks on Twitch, thank you for asking questions. I can't always see your messages because I'm paying attention to messages that my students are asking on the class-specific chat. But let me try to go back and look at some of these questions as well. So this is perhaps the most active the people have ever been in Twitch chat, which is awesome. Yeah, so there's a great point being made in Twitch chat, which is that there's an assumption here that we're in the crash model, right? Not the omission model. So what if messages are lost, right? So if we were in the crash model, the algorithm that I just sketched out would work for implementing reliable broadcast. If we're in the omission model, then you would have to do something more. But it turns out that you could make this reliable broadcast protocol work in the omission model by also doing reliable delivery. So assume that every one of these messages is, under the hood, actually a reliable delivery message, which means that in practice it could be several messages and then you wait until you get an ACK. So you could combine this reliable broadcast protocol with a reliable delivery protocol, and then it would also work in the omission model. Thanks for asking. That was a good question. Right, we'll wait just a little bit longer for the quiz. Whoever said in Twitch that you have to subscribe to get your questions answered, that's not true. Yes, you can get your questions answered for the low, low price of $4.99 a month. No, if I don't answer your question, it's probably just because I didn't see it. So there's a question about what's a correct process? Right, so that depends on the fault model, right? So if we're working in the crash model, a correct process is one that doesn't crash. If we're working in the Byzantine fault model, then a correct process is one that doesn't crash and doesn't exhibit any Byzantine behavior, any arbitrary or malicious behavior. So this question of what a correct process is dependent on what our fault model is. Just like in security, when somebody says, or when somebody asks the question, is this system secure, right? Well, that question of like, is something secure, doesn't it really make sense out of context? Then you have to ask, what is your threat model, right? So just like that, in distributed systems, if you're asking, is this process correct? The question is, well, what are the ways for a process to be incorrect? And so that means we have to ask, what is our fault model? Okay. So the last thing I want to talk about today in the few minutes that we have left coming back to this idea that fault tolerance often involves making copies. So we can mitigate message loss by making copies of messages. We've seen that. But what else other than messages do we have to be worried about maybe losing? Well, in addition to message sends and receives, right, there's also internal events that happen on processes. These dots that don't have any arrows connected to them. And as we've talked about, those internal events correspond to state. Somebody just said a perfect word in chat, which is data. We have to be worried about keeping data. So processes keep state, or equivalently, processes keep data, right? So if we're mitigating message loss by making copies of messages, How do you think we mitigate the loss of data? Well, we can make copies of that too, right? So maybe these processes have a friend who's tied to them and who has the same data. Or in other words, replication. So one thing that we talked about early in the course, right, is that if we have a process and that process has some events on it, we can think of each of those events as being a state. And whatever our state is at a certain point in time is determined by all the events that have happened up until then. And we also have some process local memory, right? Like maybe we have a process, and this process happens to know that x equals 5. Now that might be because it received a message that said set x to 5, or maybe it got a message that said set x to 1, and then it got 4 messages that said increment x by 1. But for whatever reason, its current state is that x is 5. Maybe it's an entry in a key value store, like the one that you're implementing if you're taking the class for credit. So we can replicate this thing with all of its state. So mitigating data loss is one reason to do this. It's probably the most important reason. So now, if one of these crashes, the fact that x is 5 isn't lost forever. So that's the most important reason to do replication. Are there any other reasons why you would want to have another copy of a process aside from fault tolerance? Performance, yeah. So one reason is, let's say I'm here at home and I'm in California and I want to make a request to this key value store, which is running on a machine in Australia. So let's say this one is in Australia. Or I could make a request to its replica, which is in a data center just down the road from me. The request to the data center that's just down the road from me is probably going to be faster. No promises, right? This is the internet. Everything's asynchronous. But it's likely that the physically closer machine is the one that I will hear from faster. So one thing that you can do is make a bunch of replicas and put them in different locations around the world so that they'll be close to the clients that need them. And so then you get good data locality in addition to fault tolerance, right? And then another reason to do replication is just dividing up the work, right? If you're getting a lot of messages, let's say you're getting a lot of requests for the value of x, and you're having a hard time handling them all, often it makes sense to have another machine to take some of the burden off of you. So those are all reasons to do replication. What we haven't talked about yet is the significant downsides to doing replication, and that will be what we begin with next time. So I'll see you on Friday.